Okay, so welcome once more. It's only one lecture left, so this one and the one next week before the exam. Lecture 15 of Introduction to Quantum Optics. So let me review a little bit what where we were. Maybe you remember that what we were doing was analyzing. So after spending a long time studying how is the description of a system that is not closed but open, interacting with an environment and so on. In this chapter, what we were studying is how we analyze the radiation that is coming out of the system into the environment, where the observer is kind of tracking this field that comes out, so what we call the output field. So essentially, the first thing that we did is giving an expression to the field radiated by a cavity, by an open cavity, what we call the output field. And in particular, we saw that this output field, we can write it at some position outside the cavity and where the detector is and so on, and at some time, we can write it as a function of a single annihilation operator, B out, so the output operator, that is a superposition or the interference between the input operator and the reflected input and the field that is inside the cavity and is going out through the partially transmitting mirror. So this is what we call input-output relations. And an important thing is that we saw that this is actually an annihilation operator because it satisfies canonical commutation relations, but now in time, just like the input operator, okay? So this output operator satisfies canonical commutation relations in time. And we also saw that the theory that we have created, it's a causal theory. So it doesn't violate causality in the sense that the operators inside the cavity depend on the input operator only in the past or the present, but it doesn't depend on what is the input operator in the future. And a similar thing happened with the output operator. The output operator depends only on cavity operators that are either in the present or on the past, but not in the future, okay? So this is something that we managed to prove in a certain way, actually giving an alternative expression for the output operator. But we will not use this expression anymore. So it was just to let you see the proofs and so on. And then we did the same, or at least I just enunciated the same for an open atom. An open atom meaning when you put an atom in free space and then you just let it interact with the electromagnetic field of free space. So what we saw, the first thing that we saw is that now there are, let's say, twice the number of environments of the number of the ones in the cavity, because essentially the atom is interacting not with just modes of a given frequency, but modes of a given frequency and a given propagation direction. In this case, they are independent, okay, in free space. As we saw in the previous chapter, modes propagating to the left and to the right are independent because they are not coupled through any boundary conditions. So then what I showed you, by the way, I think here I wrote A, but I meant the electric field, okay? So what I told you is that the electric field radiated from the atom can also be written as a function of an output operator. And in this case, the output operator can be written in terms of, again, the input operator and the operators of the system, which in this case are atomic operators. So in particular, the lowering operator of the two-level system, so the corresponding Pauli operator. And now the coupling, we get half of what we were getting in the cavity. So we have, instead of 2 times the decay rate, we have only the square root of the decay rate. And this comes from the fact that now when you are observing at one position, the radiation that comes towards you, you are missing all the radiation that comes in the opposite direction, okay? So this is why I also want to kind of give you this example, because here you see what happens when you are observing only part of the radiation that is that is sent around by the system, in this case, the atom. Okay. Then I think that, yeah, we still managed to go through a bit of how is the typical measurement in quantum optics, or the most fundamental type of measurement that we do in quantum optics, which is called photodetection. And essentially, I show you the basic scheme. And as a summary, the most important thing for you to remember is that you have the system radiates output light. And now what you do is that you use a photodetector that essentially turns this light that comes out of the system into a macroscopic and measurable current that we call photocurrent, okay? And this photocurrent, it's created always by something related to the photoelectric effect. And I explain you in detail the stages of a typical photodetector, but there are many types and so on. So this has to be taken just as a sketch and as intuition of how the photocurrent appears from the photons of the output light. But what's important is that this photocurrent is a stochastic signal. So if you put there, if you measure the electronic current, you will see that it just oscillates like kind of randomly. But what's important is that if you analyze the statistics of this photocurrent, in particular multi-time correlation functions or moments of a given order, and then what you see is that those statistics or those objects are proportional or encode the information about the statistics of a specific operator, which is the number operator associated to this output field, okay? And the exact relation is this one in which the multi-time correlation functions of the stochastic signal of the photocurrent are proportional to the normally ordered moments of the corresponding output number operators. So something that I didn't mention, I forgot, is the interpretation of this output number. So actually, it's not difficult to show that this operator, okay, encodes the number of photons that come out of the cavity, okay, per unit time. So it's just like that. So the expectation value of this gives you how many photons are coming out of the cavity per unit time. Okay, that's important for you to remember. Like you will have in the notes some kind of explanation why and so on. But I think it's also kind of intuitive. Actually, if you look at the definition of the output operator, for example, let's take it for the cavity, like from here, then you kind of see that if you take the number operator, so b dagger b, then you get the number operator of the cavity times gamma, right? So that's kind of the rate at which photons are coming out of the cavity. So just for you to have an intuition of what is the meaning of this output operator, and in particular of the output photon number operator. Okay, then what I argue, well, after I did some kind of combined notation for all cases, for the atom and for the cavity, so I remind you just a little bit that we will be using this notation all the time. So I just remind you that when I say the system, I mean the open system, so either the cavity or the atom or any other system we work with. Then I will call operator S to the operator that describes how do you remove excitations from your system, which in particular, we have the annihilation operator for the cavity and the lowering operator for the two-level atom. Then we will call environment to the external field or free space for the atom, so where radiation is emitted by the system. Then I define a kappa that it's either 2 gamma or gamma for the cavity and the atom. And therefore, the output operator in both cases takes this form, okay? Just the square root of kappa and then the system operator minus the input. So that's the output. And then I told you that it's very convenient to work instead of with the B operator, so the B output, which includes also the coherent part or the lasers that we are driving with the system, so the ones in the input. It's interesting to define an A operator, so an output operator, that in which we discount already the coherent part of the input, okay? So in particular, we already did that in the previous chapter in the Heisenberg picture, that we defined an input operator in which we discount this kind of coherent part. And then the relation is exactly this one between that output operator and that input operator, okay? So you will see in a second why we do this. But essentially, what then I told you is that the most general type of observable quantity that we can measure if we combine photodetectors and taking your beam and splitting it in different parts and combine it with lasers and so on. So as we will see by examples, the most general observable quantity that we have access to is this kind of correlation function, okay? In which we have n dagger operators at different times. Then we have m non-dagger operators at different times as well. And that's a correlation function in normal order, as we saw, that we care about. And because the output operators at different times commute, we can even assume that this is going to be very useful in the following, that we have time ordering. So this means that, well, exactly this thing here. So the operators act on the state in chronological order, okay? So the one that is in at a smaller time, so at the previous time, acts first on the state in this expectation value, okay? So this kind of correlation functions, the first one who developed this kind of correlation functions, or that understood that these are the correlation functions that are important when characterizing quantum mechanically or even classically the light field that is radiated by systems, was Glauber in 1963. So in these famous papers that he published, that actually marked the starting point of theoretical quantum optics. This is the papers where he also made the connection with coherent states and all these things, like we discussed at the beginning of the course. And actually, this work was so important that he was awarded with the Nobel Prize for this and other contributions, but essentially for starting the serious study of theoretical quantum optics. Okay, so I think that this is where we were. Yes. So let me then continue. And the first thing that I want to talk about is, okay, now we understand that these field correlation functions are the most important object, but how do we evaluate them, okay? So how do we compute these correlation functions? So of course, so, well, let me write. So how to compute these functions? And then, so in the most general case, so by general case, I mean that the environment is in a thermal state and you have lasers driving and all of this. Then in this general case, the only thing that you can do is you solve, so using, for example, the quantum Langevin equation. So you find S of t, so the operators of the system, as a function, or better, a functional of the input operators, just like we saw in the previous chapter, and then we use the input-output relations. Okay, so that's the best we can do. So we need to evaluate the expectation value or some kind of statistical object related to the output operator. So we just write the output operator in terms of S and A in. We know the statistics of A in. We know the relation between S and A in, and therefore we can evaluate this object here. So that's the best you can do in a completely general situation. And actually, in an exercise that I will give you, but you don't need to do as homework, you will just have the solution. So you see an example of this. This is what we will do. However, it's also very interesting to consider a special case that in optics, it's kind of the normal case. So I call it a especially simple case, which is the case in which the temperature is equal to 0, or better, that the number of thermal excitations around the frequencies of your system, of the radiated field that you care about, is 0. So this is actually the situation that you have at optical frequencies in our room temperature experiment. So this is why this situation, even though I call it kind of a special case, in optics is what you usually have. So in this case, what's very interesting is that you can just relate the output correlation functions. So the output correlation function of order nm that goes from time 1 to time n plus m, okay? This you can write directly as something proportional, and the proportionality factor is just the decay to n plus m over 2. Another correlation function that I will just call G without the out. Okay, and what's important is that this correlation function, as you can imagine from the name, this correlation function is just the same type of statistical object, but instead of for the output field, for the cavity field or for the cavity operators. So in particular, you will have this kind of object. Okay, so these are system correlation functions. Okay, so this is very nice because we usually solve through the master equation or through the quantum Langevin equation. We know the properties of things inside the cavity, right? So things of the open system. And this gives you the relation between the statistics inside and the statistics outside that we observe. And as you see, when we have 0 temperature in the environment, then the environment that we are using to observe, remember that that doesn't need to be exactly the same as the environment that we are using to drive the system. So if that happens, then we have this simple one-to-one correspondence. And let me show you the proof because it's very simple and it explains why we chose things in the way we did when we wrote these correlation functions. So first of all, the idea is very simple. So how to prove this? It just comes from time order. So the fact that we have time order, so that we have order in time chronologically these operators, and causality. So thanks to these two things, and I remind you that causality simply means that the input operators commute with the cavity operators if they are in the future. So for t prime larger than t. Okay? So with these two things, this means that when we come to expressions such as this one, okay, this expression in here, whenever we write A out in terms of S and A in, we will have products, okay, of S dagger operators with A dagger operators and S operators with A in operators and so on. But we can always, thanks to the fact that we have time order and we have this commutation relation, so the input commutes when it's in the future of the intracavity, then this allows to reorder. So it allows reordering all expressions. So wherever expression that you get that combines intracavity operators and input operators. So wherever expression that involves inputs, we can always reorder it in a way that we always have one input operator dagger on the left, or saying this is equal to 0, or we have an input operator, annihilation operator on the right. Okay, this is completely trivial. And now the point is that if you are at 0 temperature, then you have the annihilation operator acting on vacuum, okay, the vacuum of the external field, which is 0, or in here you have the same, but in the dagger direction, let's say, in the left direction. So then the only contribution in this expression that remains is the one in which you don't have any input operator. So for any expression in here in which you have at least one input operator, that will give a 0 contribution if you are at 0 temperature. However, you are left with the contribution that has all intracavity operators, and that each intracavity operator contributes with the square root of kappa, okay? And you have n plus m, so then you are left with n plus m over 2 for kappa, and then the corresponding correlation function for the intracavity modes. So this is an extremely useful expression, and it's actually what we are going to focus on from now on, is this intracavity kind of correlation functions, okay? But keeping in mind that we can measure them in an easy way. Okay, so before we actually start studying examples, which is what we will do for the rest of the class today, let me introduce something that we will call the normalized correlation functions, which essentially are motivated by the following fact. So I think it's kind of clear after the interpretation I gave for the output photon number operators that this correlation function, G of n of order nm, will be larger in absolute value. So it's a larger object, or it has a larger value. The larger the emission is from the system, right? So, and as I say, think as the simple example, imagine that you care about this G11 of the same times, which is nothing but the expectation value of the output number operator. Okay, and as I told you, this just gives you the number of photons radiated per unit time. So therefore, if you have a system that is radiating a lot, so it's sending a lot of radiation out, this will be large. If it's sending only one photon from time to time, then it will be very small, right? So, but what happens if we are not so interested on how much the system radiates, but we are interested on kind of comparing the properties between systems that might emit at very different rates, but we would just want to understand which type of light it is emitting. So it is emitting single photon wave packets or coherent light continuously, or it's a thermal source, which kind of source it is. So if we want to do that, so if we want to compare sources that have different emission rates, so if we want, oops, let me write it down. So if we want to compare the properties for example, like the ones we are studying here, the time correlators, or the corresponding spectra and whatever we want of sources that have different emission rates. So then for doing this, we define a normalized G function that we will call small g, G of order n, that will depend on 2n times, as you are going to see why. That is just the corresponding G of order nn, so we do it only for even orders. You can also define meaningful normalized correlation functions for orders that are not even, but in order to not complicate things and because we don't care about those in this particular introduction of quantum optics, I will not talk about them. So essentially we have the corresponding correlation function of order nn, okay, at 2n times. And we just, the only thing that we have to do is just we normalize it to the total rate of emission that we have seen, that is the G11. So the rate of emission of photons at each particular time. So we have 2n emission rates. Now we can write like this. Oh, sorry, this is not 1, but 2n. Let me write it again. Okay. So now it's clear that whenever a source emits more, then it will be normalized more strongly. And essentially all the correlation functions now will stay bounded by between 0 and 2 or something like this, as we are going to see. Of course, we can do the same for the correlation functions of the system. So of the system operators. So exactly the same kind of expression, but removing the out label. So let me write it down. So we will have this, and then we normalize it to the corresponding intracavity correlation function. okay? And of course, we know that these two now are equal, not proportional, but exactly equal if, so this is for when you can approximate the number of thermal excitations to 0 and you are time ordered. So that's important. So this expression needs to be time ordered. So that's already from the previous definition that we made, but I just want to make it clear again. Okay, so then what we will see now is that, for example, whenever you have sources that satisfy that all these correlation functions, G of order n, are equal to 1, okay, for all times, then this tells you that no matter what is the emission rate of your source, it is emitting coherent light. So it's a laser-like kind of emission, okay? So this is actually one of the motivations of why Glauber did this. And something similar happens with thermal light, okay, as we will also see. So we can characterize whether a source is coherent, thermal, or is sending single photons out just by the study of this kind of normalized correlation functions, okay? And this is what I want to kind of explain in this class today. Okay, so then if this is clear, then now we have to talk about, so we have been doing everything in Heisenberg picture, right? So all the expressions that I am writing, it's everything in the Heisenberg picture. This is the most convenient picture in order to discuss this kind of input-output theory and so on. Like from a theoretical point of view is the most convenient. But on a practical level, it's actually useful to be able to evaluate things in the Schrodinger picture, because as we saw, usually the master equation and so on, it's more useful, or you have more techniques to attack it than the quantum Langevin equation. So then in this chapter, or in this section, I will just give you a couple of practical things related to this that are called the quantum regression theorem and the quantum regression formula. And we will see that these are actually very useful in open systems to evaluate correlation functions. So again, the motivation of all this that I am going to tell you is the following. So what is the connection between the Heisenberg and the Schrodinger pictures for these kind of correlation functions that we are writing. So GNM output, or just in the cavity, or whatever. Okay, so maybe since we are going to talk mainly about intracavity, I will focus on that. Okay, so this might sound like, I don't know, like something that is just technical and of practical interest, but we don't learn much physics from it. But as we will see, actually, learning about this will allow us to give some kind of interpretation to the correlation functions and so on. And then it's really of conceptual relevance as well. So in particular, I am going to focus, so everything I am going to do can be generalized to any correlation function GNM, but I am going to focus on one type of correlation functions that we call two-time correlators, okay? And two-time correlators, the most general type of two-time correlator, I can always write it in the following way. So I just take one system operator A at time t, and then I find what is the correlation with another system operator at time t plus tau, so a different time, okay? And then I check, so I also add one more operator C at the original time t, okay? So it's important that these operators A, B, and C are arbitrary system operators. okay? And of course, this is a Heisenberg picture expression because these are operators that depend on time. And now the question is, okay, if I want to focus on this kind of object, and by the way, I will assume that tau is positive, okay? So therefore, you see that, for example, if C is identity, then you are evaluating the correlation function between A and B in the future. Or if A is identity, then you are evaluating the correlation function between B and C, where B is in the future of C. So C is in the past of B, okay? So it's AB with B in the future or BC with C in the past. So this is the kind of correlation, two-time correlation functions that we care about. And then the quantum regression theorem tells you that you can write in the Schrodinger picture this two-time correlation function in the following funny way. And as I say, we will give it an interpretation soon. But let me write it down and then just explain you the general meaning. So this expression here is known as the quantum regression theorem. Okay, and I remind you that this L that appears in here, this is what we call the Lindbladian. And in particular is the superoperator that defines the master equation. So your system, your open system satisfies some kind of master equation in which is generated, or the dynamics of the state is generated by a superoperator that we call the Lindbladian or Lindblad superoperator that we call L, okay? So then what you see is that this correlation function in here, so this two-time correlation function that we can measure in the lab appropriately, and it's equal in the Schrodinger picture to just taking the state at time t, operating on the state with the operators C and A, then evolving the corresponding operator according to the master equation for a time tau. So this is a linear equation, the solution of which is just the exponential of L tau acting on the state at time 0, right? So this exponential of L tau is nothing but the time evolution superoperator of your master equation. So then you just evolve the modified state by these operators A and C on the extremes. And then you evaluate the expectation value of that object of the operator B when the state is that object that is not a state in general, is not even normalized. Okay, but this is how you can evaluate two-time correlation functions in the Schrodinger picture. And as I said, you can generalize this expression for any kind of time correlator that you care about. So I will not do the proof of this because it's a bit technical. And even though we could learn something from it, I think we don't have too much time. So I will just skip it. I prefer to show you some examples. And in any case, you have the proof in the notes. So if you are interested about it, you can go and check it. And just let me do one remark on notation. And the remark is that we are not going to do explicit differentiation between the Heisenberg picture and the Schrodinger picture in the following sense, that whenever I give you a state and I write explicitly that it depends on time, then of course, this is a Schrodinger picture state. Okay, so let's say it's a Schrodinger picture, so it's a state in the Schrodinger picture. Now, if I just write rho without a time label, then this will be a Heisenberg picture expression. So it's a state in the Heisenberg picture. So similarly, if I give you an operator A, so A, B, C, and so on, and I don't write a time label, then this means that this is a Schrodinger picture operator. And if I write the label explicitly of time, then this means that I am talking about a Heisenberg picture operator. Okay, but I'm not going to do this thing that sometimes is done, that if you want to say that this is in the Schrodinger picture, you really put an S or you put an H if you want to say it's in the Heisenberg picture, okay? This is something that we are not going to use, because from the context, it's obvious when you are working in one picture or in the other. Okay, so now you know how to connect like Heisenberg picture correlation functions with Schrodinger picture expressions, and as we will see, this is going to be very useful. But now I will give you one more useful thing, that is the following. So just imagine, so consider that you have your open system and you find a set of operators, call these operators B. So you have B1, B2, all the way until BL, for example. So you have L operators that you collect in a column vector. And imagine that you find this set of operators that is a closed set. And what does it mean that it's a closed set? It means that if you evaluate what is the evolution equation for the expectation value of these operators, they form a closed set of equations. So you can write it as some kind of linear system like this. Okay? Where this object here, of course, will be an L times L matrix. Okay? So this is very nice because this means that you can find the evolution of the expectation value of these operators just by solving a simple linear system. And maybe this looks a bit kind of specific, but actually this is always possible. So you can always do this. In the worst case, with a number of operators that is on the order of the square of the Hilbert space dimension. Okay, and this is obvious because the density matrix, okay, so the representation of your density operator in your Hilbert space has a order square of the dimension elements, and that's the master equation. Okay, so then in the worst case, you can always choose as operators, let's say the corresponding objects whose expectation value are the corresponding entries of your density matrix, and that gives you a linear system, okay? However, what's interesting is that in many systems, or under some approximations, you can find a set of operators that it's even of smaller number than the square of the dimension of the Hilbert space, okay, in which which satisfy this kind of closed equation for the expectation values. Okay, so if you have found this, then the following result can be proven, and it's super useful for evaluating correlation functions, which is that the time derivative of the two-time correlator that you are interested about, but again, this can be generalized to higher order correlators. So imagine that I tell you what is the two-time correlation between some operator A, my operators B, and then another operator C. Okay, so here I have L correlation functions, one for each B, okay? And among those, there is a one that I care about, for example. So then it's funny that the correlation function satisfies exactly the same equation as the expectation values. So let me write it down. Okay, and this is known as quantum regression formula. As you can imagine, it can be proven from the quantum regression theorem. And you might think, oh, but this is too trivial, no? Because, I mean, this means that if you have solved the evolution or what is the expectation value of the B operators, then you automatically know what is the expectation value. So what is your two-time correlation function? That's partially true, but not quite, because the initial condition of these two equations is very different. So mind the initial condition. So I call it initial with quotation marks, because as you see, we are doing the derivative in the time difference tau, but we still have the label t, okay? So then in this equation, when we talk about what is the initial condition of this equation, is actually so the expectation value of A, B, C at time t. Okay, so for tau equals 0. So then if you want to know what is the two-time correlation function of A, B, C, what you need to do is you solve a linear system. That's very nice. But with initial condition that in which you need to know what is A, B, C at time t. But still, this is so it's a very useful expression, as we will see with one example now. And just a final remark before we actually start with using these kind of expressions. So usually, as we have discussed already in the previous chapter, what we will care about is asymptotics. Okay, asymptotics meaning when time goes to infinity. So in particular, in the previous chapter, what we were saying is that when the Lindbladian or the master equation is time independent, then when the time goes to infinity, we expect the state of the system to relax to something that we call the asymptotic state, or in the case of a time independent system, a stationary state. Okay. And the important property of this stationary state is that when you do the time derivative of the state, or the same as saying that you apply the Lindbladian onto the state, because the time derivative is generated by the Lindbladian. So the time evolution is generated by the Lindbladian, then that's 0. Okay. Then essentially what I am saying is that in these conditions, the limit when t goes to infinity. So we care about the limit when t goes to infinity of the two-time correlation function. Note that this is a very interesting thing. Like, we can bring the time to infinity. So this is the observation time, but the time delay between the operators, even though the time goes to infinity, we can still make it whatever we want. So in an experiment, this simply means that you are checking correlations between your photocurrent at some time and your photocurrent at some previous time or some later time. But you do it after waiting for the system to have relaxed to the steady state. So you wait for the system to relax to the steady state, and then you measure this two-time correlation function. So this is the object that we will care about. And then in this case, just if you go to the quantum regression theorem, you see that if you take the limit of time going to infinity, in the Schrodinger picture, time appears only in the state. So then what you get is this formula, but with this state, instead of depending on time, being the steady state itself. So we get an expression that looks like this. So it's a trace of B, then the evolution induced by the master equation during the delay time, acting on, and then this was C, steady state A. Okay? So this is it. And of course, now, if you ask what is the initial condition of the quantum regression formula, which is the expectation value of A, B, C at time t, now that we care about t going to infinity, this is nothing but the trace of A, B, C in the steady state, okay? So it's the expectation value of ABC in the steady state. And well, you can see it also from this expression. When you put tau equals 0 and you use the cyclic property of the trace, you get ABC trace with the steady state. Okay? So this is for tau equals 0. Okay. So this gives us interesting connections for the evaluation of, so connections between the Heisenberg and the Schrodinger pictures for the evaluation of two-time correlation functions. And one final important remark is that even though here I am all the time talking about the extreme Heisenberg or Schrodinger pictures, you see in this formula, because we have a trace, okay, that you can change to any picture, intermediate picture that you like, and the formula will remain the same. So what I am saying is that you can also evaluate the two-time correlation function in the picture that you like the most, and in particular, you will have exactly the same expression. So you just have to change the operators to that intermediate picture, the state to that intermediate picture, and the Lindbladian, so the master equation, to that intermediate picture. So if you change everything to the intermediate picture, then you are okay. You get the same kind of object. This is very useful because in some pictures, the Lindbladian will be easier than in others, okay? Like we have seen in the previous examples in the previous chapter. So then instead of having to work in the original picture, you can move to the picture that you like the most, where your Lindbladian looks the easiest or whatever, okay? And we will see with examples now. So then in principle, you have to keep this in mind, okay? That you can do this in the picture that you like. Yeah, of course, I talked about the quantum regression theorem and the quantum regression formula for Lindblad operators that are time independent, but you have the same expression for time-dependent Liouvilleans. You just have a more complicated propagator because now it will be a Dyson series expansion, just like for a time-dependent Hamiltonian. In the notes, you will have it in general, but here we just care about the time-independent case because we will work always with time-independent Liouvilleans, or sorry, Lindbladians, like we have done in the previous chapter. So we will see this with examples now. Okay, so now we will move to the interpretation of this two-time correlation function, and you will see that in general, you can describe or interpret in the same way any type of photocurrent correlations, but maybe we can make already a short break and meet again at 2. So we can meet in 10 minutes, okay? So let me pause. Okay, so welcome back everyone. Okay, so let's start with the interpretation of the photocurrent correlators. And well, I give you the interpretation of the first order one, but that one, it's kind of trivial. So by first order, I mean the correlation function or the statistical first order moment of the photocurrent. And we have seen that in particular in the steady state, so for long times, this is what you can measure in your photodetector, but we have seen that this is proportional to, in principle, with the output operator, but assuming that we have a zero temperature environment, then this will be just proportional to S dagger of T, S of T. So the expectation value of that. And what is this? So this is very trivial. So for the cavity, this is just A dagger A. For the two-level system, this is sigma dagger sigma, and the expectation value of sigma dagger sigma, we will see it explicitly now, but you might remember from before, is just the probability of being in the excited state. So then this is just the asymptotic number of excitations in the system. Okay? So then the first order one, it's kind of trivial. Now what happens with the second order one? And here is where we will start seeing interesting stuff. So again, we care about limit when t goes to infinity, but now we are going to see what happens when we have the correlation between the photocurrent with itself, so with the photocurrent at a different time, okay? Now we have seen that this is proportional, again, assuming that we have, so the time is larger or equal to 0, and that the number of excitations, thermal excitations, is equal to 0. We have seen that this is just proportional to the limit when t goes to infinity of this correlation function of S dagger of t, S dagger of t plus tau, because tau is positive, so this is in time order. Then S of t plus tau and S of t. Okay? Then this thing in here is what we have called in the previous definition of correlation functions, the G2 of time t, t plus tau, t plus tau t. Okay? And because we are going to use it for the rest of the lecture, I will give a name to this specific correlation function. So G2 of times t, t plus tau t in the limit of t going to infinity, that we will call G bar 2 of tau. And sometimes you will understand why in a second. I will call it the coincidence correlation function, okay? Because as we are going to see, this gives kind of the coincidence of photodetection. So the probability of coincidence. I will explain this in a second. But the important thing I want to express about this is that this two-time correlation function of the photocurrent, okay, stochastic correlation function, it's equal to something that it's in the form that we have introduced before, this ABC. In particular, this operator here will be A, so A of t. So if you want, well, I put it like this, A of t. This operator in the middle will be B of t plus tau, and this operator in this extreme will be C of t. Okay, so it's a two-time correlation function of the type ABC that we have written before, where A is just the creation operator or the raising operator, B is just the number operator, or the sigma dagger sigma operator, which is kind of it's proportional to sigma set. And then the C operator is just the annihilation or lowering operator. Okay. So now, what I am going to do is I'm going to show you that this kind of correlation function that appears very naturally from just the two-time correlation, stochastic correlation function of the photocurrent has a very concrete interpretation. And I am going to do it for the atomic case, because it's the easiest, but you can do something similar for the cavity and so on, and for a generic system. So in particular, let's concentrate now on this for the two-level system. So for the two-level atom. So what is this G2 function? So in the case of the atom, and using the quantum regression theorem, so I remind you, S is just the sigma Pauli operator, so the lowering operator. And using the quantum regression theorem, we have to put B. So B would be sigma dagger sigma. Now, the time evolution induced by the master equation during the time delay tau. Now, the operator C, which is sigma. Then the steady state, because we are in t going to infinity. And then the operator A, which is sigma dagger. Okay? Now, so maybe just to make sure, remember this kind of two-time correlation function with ABC, it's equal to this kind of Schrodinger picture object. So in particular, here we have it for the asymptotic time. So when this is the steady state, and then applied to the situation in which A is sigma dagger, B is sigma dagger sigma, and C is sigma, then we get this expression. But now this is super easy and super nice to interpret, because, well, this sigma operator, I remind you, is the lowering operator. So this is ground excited. This is the raising operator, so it's excited ground. And therefore, this operator here is nothing but the excited projector. Okay? Then now we see that this expression, if I just apply these two matrix elements onto onto the state rho, this is just equal to excited rho excited, and then we are left with the trace of this acting on the G. Okay, so the time evolution acting on the projector G times, so trace with the projector excited. But we already have seen many times that the trace of a projector is just the expectation value on that state. So this is just my way of telling you that I can rewrite this in the following simple way. Okay, so I didn't do anything. I just used the definition of the raising and lowering operators. But now this expression is really interesting, because this thing in here, it's just that the population in the excited state. So is the E population. So this is the excited state population in the steady state. And this we will call PE bar, okay? So it's just the excited state population that you reach if you just have your open system, you let it equilibrate. It equilibrates to some state, and in particular to some excited state population, and that's this quantity here. So it's a probability of being in the excited state after you wait for a long time so that the system has relaxed. Okay, and now what about this one in here? So this one in here is even more interesting, because look what this is telling you. So this object in here, it is indeed a state, okay? And in particular is the state that you get when you start from the ground state, because this is the ground state projector, and you apply the evolution during a time tau, okay? So you see that this whole object here, so the object in between the excited state expectation value, is just the state at time tau, okay, when you started at time 0 in the ground state. And then when you now calculate the excited state expectation value, this is just the excited state population at time t, sorry, at time tau, when starting from the ground state. Okay? So in total, at the end of the day, what I am saying is that this kind of second order correlation function is just a product of the probability of being excited once you reach the steady state times the probability of being excited at time tau if you start at time 0 in the ground state. Okay? Very simple. So this two-time correlation function has this kind of. So this is already quite satisfying because it allows us to really simplify in a huge way this kind of correlation function. However, we can, so let me even give it more physical interpretation. So first of all, when the atom is in the ground state, I think that you would agree with me that there is no emission. Okay, so if imagine that your atom is in the ground state, then clearly there is no radiated field, because if the field is in vacuum and your atom is in vacuum, then there are no excitations to radiate. So this means that there will be, if you have the detector outside the atom measuring the radiation, there will be no click. Okay, so when I say click from now on, I will always mean, so let me go to the photodetector. So click means that you create one photopulse, okay? So that's what I mean by click. So it's just a funny way of saying that if you have a photon that is absorbed by the photodetector and then one photopulse appears in the photocurrent, then the detector will just inform you, will tell you click, okay? So similar to the Geiger counters for radioactivity. So then if you agree with me that when you are in the ground state, there is no emission, then you have to agree with me as well that the probability of being excited, that the atom is excited, so this is a system quantity, not a detector quantity, but the probability of being excited is equivalent to the probability of having a click. Okay? And what's more important, whenever you find a click, so whenever your detector has done click, you know that after the click, just by the postulates of quantum mechanics, the system has collapsed to the ground state. Well, okay, so you start with your atom in whatever state it is, and then you put a photodetector. Whenever you record one click in your detector, you know that your atom is in the ground state. okay? So just with these two very intuitive facts, this allows to interpret the G2 correlation function, which is the most important correlation function in quantum optics, in the following way. So the G2, it's equal to the probability of having two consecutive clicks spaced by a time interval tau, and once the system reaches the asymptotic state. Okay? So this is the interpretation of this two-time correlation function. It's just, I wait for the system to reach the steady state, and now I start my experiment. And my experiment is just, I record the clicks in my photocurrent. So the clicks given by my detector. And this correlation function just tells me what is the probability that I get a click at some random time whenever it appears, and then another click at time tau, okay? And nothing in between. So I get what is the probability of having two clicks separated by a time interval tau once the system has reached the asymptotic state. So in other words, we kind of are talking about coincidence in the clicks, in the detections, okay? So we are asking things such as, is there a probability that I get two clicks at the same time, or will they come spaced in time, or how? So we will see that this is related to the properties of the light emitted by the source, okay? So essentially, this is what I want to tell you about interpretation. And now we will check some examples, and I hope that from the examples, you will get even a clearer intuition of what is this correlation function. Okay, so if there are no questions about the about these general things of definitions and interpretations, then maybe I can go directly to the first example, which is example of the open cavity, okay? And how is the radiation that comes out of the open cavity. So perhaps let me just remind you a little bit about the theory of the open cavity, so in particular the master equation and so on. So let me go to the corresponding section. Let me see if I see it in here. Should be here. Yes. Okay. So I remind you quickly that essentially we saw what is the master equation for an open cavity, and I hope you remember that is this kind of expression in here. So we have some driving, okay? So for a cavity driven by a monochromatic laser, okay? So we have a driving term, we have the free evolution, and then we have the thermal environment that is giving these kind of dissipators, okay? So what we did was, because this master equation is time dependent, we moved to a picture, to a rotating picture, in which the master equation becomes time independent, and it takes this form, okay? So this is the form that I am going to just copy. So let me just copy this and bring it to where we are. Okay. So then this is what we saw. And in particular, what's interesting is that this master equation is time independent. So I will call this just the time independent Lindbladian acting on the state and everything in the intermediate picture, in the rotating picture, okay? So now that we have the master equation, we can start asking how to evaluate things. And in particular, so let me just define things again, but I particularize it to this specific expression. So the G2 function that for the cavity takes the form of the trace of the A dagger A operator, or if you want, so let me just write it in this way. So I write it in the Heisenberg picture. So this is the expectation value of A dagger at T, the number operator at T plus tau, and then A at T. So this is how it looks for the cavity, the G2 function. So I just remind you quickly, the G2 function is what comes from this expression in here. So S now is A, so then B is A dagger A, B dagger on the left, B on the right. And we already saw that in principle, this is equal to the trace of, so in the Schrodinger picture of N in the interaction picture, the time evolution in the interaction picture during a time tau. Now the annihilation operator in the interaction picture, or in the rotating picture, the steady state in the rotating picture, and the creation operator in the interaction picture, in the rotating picture. Okay? Now, a couple of interesting things. Of course, when I write A of I mean exactly this. Okay, that's the rotating picture annihilation operator. And you see that it only picks up a phase, right? As we have discussed many times. Therefore, if you go to this expression and now you substitute AI as A and the exponential, you see that the exponentials cancel because you have here AI, and I, and this will cancel. So then essentially what I am saying is that in here, I don't need to write the I in the operators. So this is, oops. So in other words, this is what we call that this correlation function, this G2 is phase insensitive. So it's not sensitive to the details of the relative phase or the phase between the operators and so on. Okay, so this is how we are going to evaluate the G2 function. And what is the steady state? The steady state of this Lindbladian or of this master equation. So I remind you, this is what we already saw in the previous chapter. And I remind you that it's very easy. So in general, this is equal to a displaced thermal state. So let me write it like this. So we have a thermal state with number of excitations n, which is the n that appears in the master equation. And then with a displacement alpha, I will call it alpha tilde. And this alpha tilde, in terms of the parameters in the master equation, is nothing but something proportional to the driving rate, and divided by the losses and the detuning. Okay? So this is something that we already saw in the last chapter. So now it's very nice because we have our master equation with a time-independent Lindbladian. We have our two-time correlation function as a function of the steady state of that master equation and the evolution induced by that Lindbladian. And we know the steady state, which has a very simple form. It's just a displaced thermal state, so it's a Gaussian state. Okay? So now that we know this, it's very easy to evaluate the G2 function, and we are going to do it for two specific cases that are the extremes. So the first example, so let me call it example 1, we are going to see what happens at 0 temperature. So what happens when the thermal state is vacuum, okay? So in particular, what this means is that the steady state is just a coherent state. So let me write it like this. So it's a pure state and it's a coherent state. And then now we can evaluate the correlation function, the G2 function, in a very simple way. So let me show you this. So G2 of tau, it's equal to, just taking the previous expression, is the trace, the number operator, the evolution induced by the Lindbladian, sorry. Then the A operator acting on the state, but the state is just a coherent state. And then the A dagger operator acting on the state. And this is it. Now you see why we are using the Schrodinger picture. Because look how easy is this expression in here. What happens with alpha? Alpha is an eigenstate of the annihilation and creation operators, right? So in particular, when you have A acting on alpha, that's just equal to alpha. Then you leave the state invariant. And then when you have the A dagger operator, so the creation operator acting from the right onto the bra alpha, then we get alpha star. Okay? Very simple. So then what we get in here is alpha, absolute value of alpha square. And then we have the trace of the number operator, and then the evolution induced by the Lindbladian onto the same state that we had, the coherent state. But now, what happens with this state? This state, by definition, is the steady state of the system, which means that if you apply L onto this state, you get 0. Oops. Okay. So that's just the definition of the steady state. So if you apply the Lindbladian, it gets equal to 0 because the time derivative of that state is equal to 0. Then essentially, this means that when you apply the exponential onto the state, it remains invariant. So in other words, if this is the steady state of the system, it is of course invariant under the evolution induced by the time evolution operator, or super operator in this case. So in other words, this is equal to the trace of n and then just the state without having to evolve it. Very easy. This is then alpha squared and the expectation value of the number operator in the coherent state, which means that this is equal to alpha to the 4. Okay? So you agree with me? Look how simple it has been at the end, like the calculation of G2. It's a two-time correlation function. It looks very complicated because you have to do input, output, all these things. But in the Schrodinger picture, it's just a few lines calculation, okay? You would have done it even in one line or even in one expression if I wouldn't have gone slowly through all the steps, okay? But what's important about this expression is that you see that it's independent of time. So it's alpha to the 4 for all tau, okay? This means that in the interpretation that the correlation function gives you the probability of having two consecutive clicks separated by a distance tau, the clicks are statistically independent. Okay? So this is really, really interesting because this is telling you that the probability of getting a click doesn't depend on whether you got a click before, okay? So it's random. So every click is random. Okay, and maybe something I can mention about this as well is that this is kind of consistent, but you have to be very careful with these kind of relations, consistent with the fact that a coherent state has a Poisson distribution, Poisson photon number distribution, okay? So the photodetector at the end of the day is kind of counting the number of photons, right? And we usually find the Poisson distribution when you assume that the events that you can get are independent, okay? Independent of each other. So then everything is kind of consistent. So a Poisson photon number distribution gives you a coincidence correlation function that is independent of the delay between the clicks, okay? But you have to be very careful with this. This doesn't mean that whenever you have this property, then the light is a Poisson distribution or the other way around, okay? Okay, but then let me tell you a few more things. Then also take into consideration that the G11 function, so the first order kind of function, this is just equal, as we have seen already, to the expectation value of the number operator inside the cavity in the asymptotic limit. And this for a coherent state is, of course, alpha squared. So then putting together these two results, this means that the normalized, so something that we will define as the normalized G2 function, which is nothing but the limit when t goes to infinity of the G2 function of t plus tau, t plus tau t. So again, let me remind you, because I don't want you to get lost in the notation. So what we define as the G2 function is just the G22 of t plus tau t, limit when t goes to infinity. This is what matters. This is the quantity that appears naturally when you do the autocorrelation function or the two-time correlation function of the photocurrent. And we have defined the corresponding normalized quantities just by taking the capital G and dividing it by the G1, okay, the G11. So then it's very natural that we define, associated to this G2 function, we define a normalized one, which will just be exactly the same definition as for the G2 function, but instead of in terms of capital G's, in terms of normalized G's, okay? So, and this is extremely simple because, well, this of course, by definition is G2 of tau divided, and then we have the square root of the limit when t goes to infinity of G11 of tt, but we have this 4 times. Okay. We have this 4 times because we have 4 times t plus tau, and t, okay? And then you get the same kind of object 4 times because all of them are in the limit when t goes to infinity. So all of them are the same kind of, for the asymptotic number of excitations. So then when you put all these things together, this is equal to what? It's equal to 1. It's equal to 1 for all tau, okay? So then I think I might need a bit more space. So let me maybe do this a bit smaller. Maybe this is enough space. So then let me just make a comment. So if you extend this to all orders, so it's something that we are not going to do, but if you would extend this to all orders and not just to G2, but Gn, so G1, G2, G3, G4, so all orders, okay? And you would get exactly 1 for all of them, okay, independent of tau. It's independent of the time delay between the operators. Then you can prove at the same time. So we will not do the proof because it requires some special techniques that we didn't go through in this introductory course. But you can prove that this is satisfied only by sources with a Poisson steady state number distribution. Okay, so this is something that you have to trust me with. So if you check the definitions of the GNs, you can prove that only when the sources have a Poisson steady state number distribution. So this means that either they are in a coherent state or a superposition of coherent states. Sorry, not a superposition, but a mixture of coherent states with the same phase. So the number distribution, it's still a Poisson distribution. So whenever that happens, okay, and that's the steady state of the system, then that's the only situation in which the G functions are equal to 1 for all tau. And that was the original kind of motivation of Glauber to introduce coherent states. Because what were they observing in the laser? So when they created the laser for the first time and they started studying this kind of moments or two-time correlation functions and so on of the photocurrent when they were measuring the light coming out of the laser, this is what they were observing. They were observing that all the G functions were independent of time and equal to 1, let's say, when you normalize them, okay? And then what essentially this meant, or what Glauber put together, is that this means that at a quantum mechanical level, you are generating coherent states, okay? So this is why we say that a laser, or better, this is why we know experimentally that a laser creates coherent states, or the light that comes out of a laser, it's coherent, okay? So this is why I wanted to kind of tell you this story. I know I didn't prove much, but it's not so important to me that you know the proofs. It's more important that you know the facts, and then you can check the proofs and the story on your own if you are interested. Okay, so now we will move to the second example, but it's 2:40, so maybe we can do the break now. And then I finish the class with the 2 examples that we are going to analyze. Okay, the 2 examples that are left. So let's do a 10 minutes break. So we meet again at 3:52. So just count 10 minutes from now. And welcome everyone again. So in this first example, what we have seen is that when the steady state of the cavity is a coherent state, then the G2 function is just constant in time, and in particular, it's equal to 1, okay? Now, in the next example, what we are going to see is what happens. So example 2, when we don't drive the cavity. So there is no driving. So that the steady state of the cavity, now since there is no driving, it doesn't matter if you are in the rotating picture or not, like there is no driving that makes everything time dependent. So the steady state is just a thermal state. So what happens when the steady state of the cavity is a thermal state? So now, for example, if I ask you what is the G11 function that we need to normalize the G2 functions, so G11 of TT, which again, this is the expectation value of the photon number in the steady state. And of course, by definition, because remember that the thermal state is parameterized by the number of excitations. So that's N, okay? Which is just the photon number associated to whatever thermal distribution, so whatever, so the Bose-Einstein distribution of the given temperature and frequency that you are working with. Okay, and now to evaluate the G2 function, this is actually the perfect example to apply the quantum regression formula. And the reason why it's actually very simple, we can come back to the, so remember that we already found the evolution equation for the expectation values of the second order moments. And because the state is Gaussian, that forms a closed system. So whenever you know that your system or your master equation is quadratic, okay, so your system is Gaussian, your evolution is Gaussian, then you know that there will be a closed system of equations just for the first and second order moments, so that you can use it for the quantum regression formula. And in particular, in the example of the cavity, so let me go show you the equations so you have them in mind. I think are these ones, yeah. So I remind you that we already showed that the expectation value of the first order moment, so the time derivative depends only on the first order moment. the time derivative of a square depends only on, of the expectation value of a square depends only on the expectation value of a square if there is no driving. Otherwise, it depends also on the first order moment. And the expectation value of a dagger A, which is what we care about. Oh, by the way, there is a typo here because here we are in the interaction picture. So I correct it. But the expectation value of the number operator evolves in time according to something that depends only on the number operator, okay, for no driving. So then let me go back to where we are. And in particular, what I have just shown you is that the time derivative of the number operator, the expectation value of the number operator, it's equal to 2 gamma, the steady state number of excitations minus the number operator, okay? So the number operator forms a closed set by itself, almost by itself, because the form that we have written the closed system equations, I remind you in here, yeah, it's purely linear, so we don't have a constant term. So we say that, here, that the time derivative of the expectation value of the set of operators is just a matrix multiplying that expectation value of that vector. So this means that this equation in here, we can write it in that form if we define a B operator, so a vector of operators that it's the following. So in here we have the number operator, of course, and then we also need to add the identity. So instead of the identity, I write down just the n, so this n that is in here, and it is assumed that, of course, this n is multiplied by an identity. Okay. So this is a B, and this forms a closed, what we have defined as closed set, because the time derivative of the expectation value of B can be written as a linear system where this matrix M, in this case, is just very simple, it's minus 2 gamma, 2 gamma, 0, 0. Okay? Very, very trivial. Then, according to the quantum regression formula, this means that the time derivative of the two-time correlation function that we care about, which in this case is the asymptotic one with A dagger as A, the B that we have defined above, and then the annihilation operator. This is equal, according to the quantum regression again, so it satisfies the same evolution equation as the expectation value of B. So this is equal to M times the same. So I just copy it. Okay. And note that this thing in here is just equal to what? So we have A dagger, and then we have the two components, N and the identity, the thing proportional to the identity in the vector B. So the one with N, this is just the G2 function that we have defined. So G2 of tau. And the second one, it's even easier because this is identity. So this means that B is the identity multiplied by N. And then you are left only with the limit when t goes to infinity of A dagger A. And that's N again, that's G11. So this is just N squared. Okay. So then in the quantum regression formula, in this case, this two-time correlation function with the vector is just equal, so the components are just the G2 function that we are interested about, and then some constant n squared, okay? So then if I take the first component of this equation, so if I take the first component of this equation, what I get, it's an evolution equation for the time derivative of the G2 function that I am interested about. Okay? And it's a linear equation, so it's a very trivial equation to solve. So now, from this expression, we can solve what is G2 of time tau, okay? And in particular, we also need the initial condition, G2 of 0. So what is G2 of 0? G2 of 0 is just the expectation value of a dagger square, a square, okay? And this is very simple to evaluate because we know the Gaussian moment theorem. If you remember from the beginning of the course, like if you know that this state is Gaussian, then you can take fourth order correlation or fourth order moments and expand it in second order moments. And in particular, what you get is that this is equal to just the expectation value of a square times a dagger square plus, and then you have twice the same contribution, which is a dagger A, okay? This is 0 in a thermal state because it's phase invariant and a square is not phase invariant. And this is just n squared because it's the number of excitations squared. So then once you have the initial condition and you see that the initial condition of this equation is just that G2 of 0 is equal to 2n squared, then you can solve it. It's a linear equation. We know how to solve linear equations. We have done it many times, and I gave you a general expression. And you can find very easily that the normalized G2 function for this thermal case, it's equal. So again, it will be G2 of tau divided the G11 to the 4th square root of that. So this is n squared. So if you evaluate this quantity, you will find that you can write it in this very simple and nice way. 1 plus exponential of minus 2 gamma tau. And this expression is really interesting because now this is telling you that if you plot the G2 as a function of tau, what you get is the following. So let me try to make it more or less accurate. So at tau equals 0, you start at 2. And at tau equal infinity, the exponential has decayed and you go to 1. So then you get an expression or you get something that goes like this, where this width in here is of order gamma, okay? So, but what's interesting about this expression is that this is telling you that it's more likely that you get simultaneous clicks. So remember the interpretation of this correlation function. It's just the probability that if I get a click at some time, then I get the next click at time tau. So this is saying that for a thermal source, it's more likely that you get the two clicks together than that you get them separate, okay? And this is a phenomenon that we call bunching. Okay, and it was first explained in a way that was satisfactory for all theoreticians by Glauber after developing this theory or beginning of the theory of quantum optics. Okay, so in particular, this is a phenomenon that was observed by Hambury, Brown, and Twiss. So maybe you have heard this name if you have read some books of quantum optics, when they were actually measuring the light coming out of the stars, okay? So they were measuring with photodetectors and they were doing coincidence and correlation functions of the photocurrents of the light that comes from the stars, okay? And what they observed was this kind of bunching effect that was a bit of a puzzle at the beginning. People were not completely sure how to explain it. And it was not until Glauber that this was explained. So the funny thing is that you really don't need quantum mechanics to explain either of these two effects, either the one that we saw in the first example or the second, because these states are very classical. You have coherent states and you have a thermal state. Okay, but it's very natural to do it quantum mechanically because the way that photodetectors work with the photoelectric effect and so on, it's very quantum mechanically in microscopically. Okay, but of course you can do a semi-classical theory of all this that works very, very fine. So this is, in the next example, we are going to see a situation in which you cannot possibly find an explanation based on semi-classical physics, okay? You really need quantum mechanics. And this is the effect that it's called antibunching, and that appears in the radiation emitted by two-level systems, in particular what we call resonance fluorescence. So this is the final example that I will discuss today. And so let me go through it. So this will be example 3. And this is the example of an atom that is driven. Again, driven by a monochromatic field. And it is radiating at 0 temperature, okay? In an environment at 0 temperature, just like we did in the example of the previous chapter. So then let me again remind you a few things about the atomic master equation and so on. So again, in a rotating picture, and this rotating picture was defined by a unitary transformation, you see. That is just the typical rotation that we talk about all the time. So this is sigma set, okay? That literally turns or makes the Pauli operators, the phase of the Pauli operators increase linearly with time, so they kind of start rotating in the Bloch sphere or whatever. Okay, so in this picture, then the master equation, I remind you that reads like this. So we have the detuning term, and then we have the driving term. And then we have a dissipation term that, because we are at 0 temperature, only contains excitations that are going out of the atom, what we call spontaneous emission. And this, in our current language, this is the Lindbladian acting on the state. Okay. Now, there are many ways in which you can find the correlation functions in this system. Again, because it's a two-level system, it's obvious that we only need 4 operators because the dimension of the system is 4. So with 4 operators, we can find a closed set. So one possible route, so I just want to mention it, even though we will not follow it, is that the operators sigma dagger, sigma set, and the identity, this form a closed set. Okay, and then you can proceed, okay? However, we are going to proceed in a simpler way. It's a way that requires only the evaluation of the excited state probability. And this is something that we have already seen when interpreting the two-time correlation function. If you remember, we saw that it's a product of the excited state probability asymptotic in the asymptotic state times the excited state probability at time tau after evolving, after collapsing to the ground state, okay? So that's what we are going to use in here. But in any case, first, let me remind you even more things. So remember that we wrote the Bloch equations of this system, and the Bloch equations in particular for something that we call B with a tilde because it's in the interaction picture. So the interaction picture expectation value of the sigma operator that we call B, so the complex Bloch vector component. And then B set is nothing but the expectation value of sigma set, which you can write, of course, as 2 times the probability of being in the excited state minus 1. Okay? These are things that we already saw when we were studying the physics of two-level atoms. Then the Bloch equations read just like this. So we have that the time derivative of B is equal to minus gamma minus I delta, B tilde minus 2 epsilon probability in the excited state. And then the time derivative of the probability in the excited state is 2 times the real part of epsilon star B minus 4 gamma PE. Okay? So then you actually see from this expression that these 2 operators, so sigma and sigma set, they form a closed set. Okay? So you also need sigma dagger because this is the real part. So you get B and B star. But these are the Bloch equations. And the first thing that we need to do is understand the steady state. So this is something that we didn't really do in the previous chapter. So I just show you very quickly that the steady state in particular, the excited state probability in the steady state, which you can find very easily because we have a time-independent master equation. So then we only need to ask what is the state that doesn't evolve in time. So we just have to set to 0 the time derivatives. And if we do that, it's automatically trivial. I mean, it's very, very simple. You see that if you set to 0 this time derivative, then you get B as a function of P. And then you plug B as a function of P in here, and you just get an equation for P that you can solve trivially. And in particular, you will find the following expression. So I just give you. So I will call P with a bar, like we already did in some previous slide, to the probability of being in the excited state when T goes to infinity. Okay? And this you can write as something that I will call capital P divided to 1 plus capital P. And this capital P is nothing but something that is just well known to you, which is this quantity here. It's kind of the Lorentzian thing that we always get when we are driving a system. And in particular, the most important thing in here is that this is proportional to the power of the laser that you are driving the atom with. And it's inversely proportional to the decay rate of the atom, so the spontaneous emission of the atom, and to the detuning of the laser that you are driving with. Okay, but then finally, what I want to discuss about this steady state is two specific limits. So the limit when P is equal to 0, which means that you are not driving, then you see that when you are not driving, when P is equal to 0, then the probability of being in the excited state asymptotically, it's equal to 0, okay? Which means that you are in the ground state of the system. That we know because that's what we saw for spontaneous emission. No matter what is the initial state of the system, if you are not driving it, so if it's just in some kind of state with some probability of being excited, in the free electromagnetic field is in vacuum, then eventually it will evolve such that it emits the atom, the excitation, sorry, in the form of a photon. And then it will just decay and it will just get to the ground state. However, this is something that we know, but the important or the new thing is what happens when P is much larger than 1. So when we are driving very hard, okay? So we are driving very, very hard, and then like out of naive intuition, one would think, oh, if you drive very hard, then you will just get it in the excited state most of the time, but that's not true. You see that in the limit of P going to infinity, this goes to 1/2, okay? So this means 50% inversion. So inversion is how we call to the property of whether, so if you are in the ground state, that's kind of the equilibrium state of the atom, and then inversion means that you manage to bring the atom from the ground to the excited state, but you do it only with 50% efficiency. And that's the best we can do. Okay. And it's very funny because imagine that you wouldn't have dissipation, okay? If you wouldn't have dissipation and you drive with a classical field, what happens? Rabi oscillations, okay? We already saw this in the 3rd chapter. So you would have Rabi oscillations between ground state and excited state and periodic oscillations, okay? Now, what is dissipation doing? Dissipation is kind of destroying the coherence between these oscillations and making them decay towards half, okay? So you can be in the ground or in the excited state periodically, but because of the noise in the system, this is shifted randomly, and then after some time, you cannot, let's say, you have lost the periodicity, and you just get an average of what you have. You could be in the ground or in the excited state, so you are in the middle, okay? So that's exactly what we find in here. So this is already an interesting thing. Just remember, keep in mind, by driving very hard an atom, you cannot bring it to the excited state, not with 100% probability. You have to do something much smarter than that in order to bring it to the excited state. Okay, that's a common, I wouldn't say misconception, but it's something that sometimes people don't realize very strongly working in quantum optics. Then now, if we go to the G2 function, so what we call the coincidence correlation function, or just correlator, then we already saw, so this is something that I already wrote before. So in particular, what we saw let me just write it down and then I show you. So this is expression that we get in general for the normalized G2 function. And then what we saw is that this G2 function, the interpretation, so let me go again to it. The interpretation of this is that the G2 function is just the probability of being excited times the probability of being excited at time tau if you were in the ground state at time 0, okay? Then on the other hand, the G11, it's nothing but this thing in here. So this is the, so if you want, let me better do it this way. So this thing in here is the G11 of TT, okay? Because remember that the expectation value of sigma over sigma, that's the probability of being excited. So this is exactly G11. So then when you put both expressions together, what you get is that the denominator is P excited square. The numerator is P excited in the steady state times P excited at time tau when initially you are in the ground state. Okay. And this, it's completely trivial to understand two specific limits. So we will talk now about the specific shape of PE of tau, but you already know what happens in two limits. So when tau is equal to 0, what is the probability of being excited if you are in the ground state? 0, by definition, okay? And when tau goes to infinity, what is the probability of being excited? Well, that's the probability of being excited when you are in the steady state. So, and you are dividing by that. So then the normalized correlation function is equal to 1. Okay? So you see that this is very interesting because you go from a situation in which at time equals 0, you have 0, to a situation in which at time infinity, you have G equal 1, okay? So essentially this is telling you that you have 0 probability of having simultaneous clicks. Okay? But that eventually, so for long delays, these clicks are statistically independent for long delays. So for large tau. So this property, it's called, as you can imagine, antibunching. Okay? And this property is very important for many reasons. But you see that, first of all, this is completely the opposite situation of what we had before. Now the probability that we get 2 clicks at the same time is 0. So if you want, you can, in loose terms, you can think that the number of photons, or the photons, come to the detector one after another, okay? So in other words, the atom is emitting single photons. And this is actually very natural, right? Because you have the atom excited, it goes to the ground state, so it by a spontaneous emission, it emits a photon. And now it will need some time to go from the ground state to the excited state again, okay? You are driving it, so you are giving it energy to go up, but it requires some time, okay? And this time delay, so this time in which the probability, or during which the probability is essentially 0 of getting a click in the detector, is just what we call the reloading time. So how much time it takes to load the excitation again in the atom, okay? But essentially, this is the most important property that comes from the emission of radiation by atoms. And the other important thing of this is that just like we showed before, or I told you before, that all the correlation functions that we were seeing, they are all classical in the sense that just with a classical electromagnetism model for optics, you can explain them. This one in here, so this antibunching, is a phenomenon that cannot be explained with classical light. So with a semi-classical model in which the atom is quantized, but not the light, okay? The light field is classical. That doesn't work for antibunching. For antibunching, you really need to go to single photons and therefore to the quantum theory of light, okay? So these are just things I want you to know, and I will write explicitly in the notes. So, but again, I am not proving it. Like, this would take a bit more mathematical technology that we didn't develop in this introductory course. So now, let me just to fill the gap, because, okay, we know what happens when tau is 0, we know what happens when tau goes to infinity, but what in between? So, of course, you can imagine that you just grow towards 1 in some way, but it's actually interesting to see how. And I give you the expression that you will find in the notes, proof explicitly for the case of a resonant driving. So in the case of driving resonantly, it's quite easy to solve the general problem. And in particular, you can write the G2 function, G2 of tau, in a very nice way. And let me just define one parameter that I will call R. And R is just 9 minus 16 P. Remember that P is the driving parameter, the normalized driving parameter, proportional to the power of the laser. And then you can write the G2 function as 1 minus the exponential of minus 5 gamma tau over 2. And then in here, we have a hyperbolic cosine of R gamma tau divided by 2 minus 5 hyperbolic sine of R gamma tau divided by 2 divided by R. Okay, so whatever, some technical expression. But the important thing is what happens, for example, when you drive very hard, which essentially in this case, that the detuning is 0, it simply means that the driving rate, the rate at which you are driving, is much larger than the losses, okay, than the dissipative rate, than the spontaneous emission rate. Then in this case, the G function reads in a very nice way, reads like this: cosine of 2 driving tau. So just check out that when P is larger than 9 divided by 16, then this is an imaginary parameter. R becomes imaginary, okay? And then you have the hyperbolic cosine of an imaginary argument, and that's a normal cosine. That's why you get a cosine. So then the G2 function of time, of the time delay, is just 1 minus a decaying exponential. So when tau goes to infinity, this goes to 0, and then you get the 1 that we knew, and then a cosine of tau. And what is the oscillation of the cosine? The oscillation of the cosine is precisely the Rabi frequency, okay? This this rate, this driving rate. So in other words, it's very interesting that the G2 function encodes, that is why I wanted to write it, damped Rabi oscillations. Okay. And why is this interesting? So for several reasons, let me just argue in this couple of minutes. So first of all, we already said that if there are no losses and you drive the atom, then you would observe Rabi oscillations. But now imagine that you are in the laboratory, you want to observe the Rabi oscillations, and you are in a normal laboratory where your atom is actually in free space, or it has some kind of environment, and it does a spontaneous emission. So now the question is, if the spontaneous emission is too fast, then we have seen that the steady state, okay, it starts oscillating, but it eventually goes back, so goes down to 50% of inversion to a steady state. So you don't see oscillations in the state anymore, okay? Does this mean that if you are not careful to prepare it in the ground state and then do a measurement very quickly such that the decay still didn't happen, you cannot observe the Rabi oscillations? No, this is the point. Instead of doing that kind of experiment, you can do a simpler experiment in which you just let the atom relax, you let it go to the steady state, you don't care to initialize it in the ground state and then observe the oscillations quickly and so on. You just let it go to the steady state, and then you just put a photodetector outside and you measure the coincidence between the clicks in the detector. And you will see that these clicks oscillate in time. I mean, as a function of the time delay, they oscillate in time as is predicted for Rabi oscillations with exactly a frequency that it's proportional to the Rabi frequency, okay? And then of course, if you wait, so if you put the delay long enough, then you will lose that kind of dependence and it will just become flat, okay? So this is kind of interesting. The probability of getting 2 consecutive clicks at the same time, so simultaneously, is 0. Then it oscillates with the delay as Rabi predicts. And then if you wait long enough, it decays towards like the coherent limit or the independent clicks limit. So this is the one of the most important and paradigmatic examples that you can find in quantum optics about this kind of measurements. And this is actually one of the, let's say, one of the experiments or classic experiments in which the quantum nature of light was kind of explored for the very first time. Because as I said, all experiments with lasers and with the light coming from the stars and so on, all that was very classical. But experiments in this direction were the first ones in which they could prove that quantum optics is really required to describe the emission radiated by quantum systems and atoms in particular and so on. Okay? So essentially, this is all I wanted to tell you for today's lecture. I hope you found it interesting. I think it connects a lot with what it's done in the laboratory, but at the same time with a lot of very deep theoretical effects and theoretical physics. So, and as usual, if you have any questions, you can ask me. Now we have a few minutes left. So I will just be waiting here for the next 10 minutes or so. So if you want to ask anything, go ahead. So perhaps I will stop recording now before I give you some